Hello and welcome dear students. Today we are going to discuss the topic hydrograph and its components. A hydrograph is a graphical representation of discharge rate of a stream with respect to the time at a specific point of time. It shows how the amount of runoff or discharge in a stream changes with time at a specific point. It is inverted U-shaped diagram. When rainfall occurs over a catchment, the water passes through different processes before reaching the stream channel and finally the outlet. As rain continues, the discharge slowly increases, reaches a peak and then decreases. The pattern depends on the physical features of the catchment, its shape, slope and the climatic conditions. All these factors control how the catchment responds to rainfall and how water flows out of it, which is shown by the hydrograph. A hydrograph therefore represents combined effect of physical, geomorphic and climatic characteristics of the basin on the rainfall runoff process. Runoff consists of surface runoff, subsurface runoff and delayed groundwater flow known as base flow. A hydrograph illustrates change in river discharge over time at a specific point and is widely used to study flood behavior. A hydrograph is a graph that plots amount of water flowing in a river against time, usually during a rainstorm. Think of it as a picture of a reverse reaction to rain, starting low, rising fast, peaking, then slowly dropping back. It comes from rain falling on a catchment area. Not all rain reaches the river right away. Some soaks in, some evaporates and some flows over land. The graph captures the quick flow from the rain and slow drip from the underground water. Hydrograph shows how river flow changes over time during and after rain, helping engineers to predict floods and plan water projects. They break down into simple parts like the rising side, peak and falling side, each telling a story about how rain turns into a runoff in a river basin. This lecture explains everything step by step in clear terms from basic to real world uses. There are three structural components of hydrograph. Let us discuss these one by one. A standard flood hydrograph is made up of three principal sections: the rising limb, the crest and the segment, the recession limb. Each section reflects a different stage of runoff response within the drainage basin. Now, rising limb, that is built up phase. The rising limb represents the initial increase in river discharge following the onset of precipitation. It represents the upward sloping part of the hydrograph, showing an increase in discharge as water gradually accumulates in stream channels and crosses the watershed. Early rainfall is primarily lost to infiltration, intercepts by vegetation and surface detention that results in gradual rise in stream flow. As rainfall persists, soil saturation reduces these losses, accelerating surface runoff and steepening the discharge curve. The form of this segment is influenced by basin properties as well as the storm's duration, intensity and spatial distribution. Variation in the physical and geomorphic features of a basin determine how rapid discharge increases. According to the rising limb may be steep or gentle depending on the factors such as basin characteristics and nature of storm, including its types and length of occurrence. Crest or peak segment. The crest makes maximum discharge during the flood event. appearing as a smooth apex or plateau on the hydrograph. This segment is critical in hydrograph for identifying peak flows which occurs when runoff contribution from the entire watershed converge at the gauging point with maximum intensity. Its form narrow spike, broad plateau or multiple summits vary with basin dynamics, precipitation, distribution and sub-basin inflows. Peak magnitude is governed by storm intensity and basin size, serving as a key matrix for flood forecasting and warning. The second major segment of the hydrograph is BPC portion and commonly referred to as crest segment. This is the most critical part of the hydrograph because it indicates the peak discharge at point P, which is essential for planning and designing of water related infrastructures. This segment is crucial for hydrological analysis as it provides the maximum flow generated by particular rainfall event. Knowledge of this peak discharge helps in determining the maximum volume of water that must safely passes through a given channel section or structure, making it a key parameter in hydraulic design. Where the point B and C on this curve are known as inflection points. Point B marks the end of the rising limb, while point C signifies the beginning of the falling limb. The peak discharge P lies between the 2 points and represents the highest flow attained during the event. The inflection point C also indicates a shift in the contribution of catchment to the stream channel. Up to this stage, runoff is mainly supplied by overland flow from the entire watershed. Depending on the combined effects of rainfall characteristics, basin properties, the crest segment may appear sharp or relatively flat. Furthermore, point C corresponds to the condition of maximum detention storage within the watershed. At this stage, storage resulting from rainfall reaches its highest level, after which it begins to decrease as discharge starts to recede. Then recession limb. The recession limb illustrates the gradual decline in discharge after the peak, driven by the drainage of stored water from the catchment, including soil moisture and aquifer. Initial rapid decline stems for surface storage depletion, followed by slower base flow from groundwater seepage. This phase persists until pre-storm levels are restored. The duration and shape of the limb are primarily controlled by watershed characteristics like soil porosity, bedrock permeability and subsurface storage capacity rather than storm rainfall pattern. Prolonged recession signal substantial groundwater reserves as in sandy aquifer. The falling limb also referred to as the recession curve extended from second inflection point of the crest segment to point D, which marks the beginning of natural groundwater flow. This part of the hydrograph reflects the gradual reduction of water stored within the basin during the earlier phase of rainfall. Once rainfall ceases, the stored water begins to drain slowly from the catchment. As a result, the behavior of the recession limb is largely independent of storm characteristics and is governed mainly by physical properties of the basin. The recession limb represents the combined contribution of surface storage, including detention and channel storage, interflow and groundwater flow to stream discharge. Essentially, this curve illustrates the rate at which discharge decreases as stored water is released from the watershed. Now, let us briefly define some time parameters associated with the hydrograph. Several time related parameters are important in hydrograph analysis. So, duration of effective rainfall. Not all rainfall directly enters a stream, only a portion of it reaches the channel and leads to an increase in stream discharge, while rest is lost through different processes such as infiltration, evaporation and surface storage. The fraction of rainfall that actually contributes to stream flow is known as the time period during which rainfall intensity exceeds infiltration capacity and produces runoff is the duration of effective rainfall. Lag time or basin lag. Lag time is the time difference between the center of mass of effective rainfall and peak of the unit hydrograph. Time to peak. This is the time interval between the start of direct runoff and the occurrence of the peak discharge. Time of concentration. It is the time taken by runoff from the most distant point of the watershed to reach the outlet. It depends on basin length, slope and surface characteristics. On a hydrograph, it is represented as the interval between the end of the effective rainfall and inflection point on the recession limb, where Tc time of concentration, L maximum length of travel of rainfall, S slope of the channel, H difference in the elevation between the most remote point in the channel and the outlet. Time base. The time base of the hydrograph is the total duration from the beginning of the runoff to the end of the recession limb. Recession time. It is the time taken from when effective rainfall stops until the flow in a river falls to its lowest point on the recession curve. Now, rainfall characteristics and shape of hydrograph. Let us elaborate this. Rainfall characteristics play a key role in shaping the runoff hydrograph, which shows how water flows from a catchment area respond to precipitation events. Intensity and duration together controls the built up and decline of stream flow, while spatial distribution determines timing and peak variation. First, let us analyze the effect of rainfall intensity and duration on hydrograph. Rainfall intensity refers to how heavily rain falls over a given time, directly affecting the volume and speed of surface runoff entering stream. Stronger downpour overcomes soil absorption faster, leading to the higher peak discharge and greater overall runoff amounts, especially once the ground becomes waterlogged. For instance, light rain might soak into dry earth without producing much stream flow initially, but intense bursts quickly generate overland flows that surges hydrograph rising limb steeply. Duration of rainfall works alongside intensity to extend or shorten the base of hydrograph. Short, heavy storm create sharp, narrow peaks that drop off rapidly as contributing areas exhaust their quick responses. In contrast, prolonged moderate rain allows water from progressive farther parts of the catchment to arrive at the outlet, building a border plateau in the hydrograph after the time of concentration of the basin phases. Imagine isochrones, which marks zone of equal travel time to the outlet. A brief storm activates only nearby zones for a quick spike, while extended rain engages the entire basin, sustaining higher flow longer without further intensity increases. Together, high intensity with long duration produces the most dramatic floods, as accumulated excess rainfall keep pouring into channels without pause. Now, let us see the effects of spatial distribution of rainfall on hydrograph. Rainfall distribution across a catchment fundamentally alters hydrograph shape by influencing when and from where runoff contribution arrives. Uniform coverage generates balanced, smooth rising hydrograph as all areas contribute simultaneously relative to their distance from the outlet. Patchy pattern, however, create skewed response with heavy rain closest to the outlet trigger immediately intense peak because short travel path deliver water fast, resembling a nearby flash flood. Farther upstream downpours delay peak until isochrone align, resulting in later but potentially prolonged flows that overlap with either inputs from compound rises. For example, if the intense rain hits only the upper basin, the hydrograph lags significantly before climbing, often yielding low peak due to spreading and temporary storage along the way. Concentrated lower basin rain spike early and high, but feeds quicker without sustained upper support. Upstream moving storm system spread contribution over time, flattening peak and widening bases, while downstream progress to pile water rapidly for sharper, taller hydrographs. These variations highlight why identical total rainfall yields different floods. There are some other factors that affect the shape and volume of hydrograph. The shape and characteristics of runoff are influenced by several interrelated factors. These factors can be broadly grouped into physiographic factors, climatic factors and human factors. Now, have a look on these factors. Physiographic factors include the shape and size of the drainage area. These also include the slope of the land surface and main channel. Features such as the shape and the size of the watershed, slope, elevation, drainage density and the nature of the valley impacts the hydrograph. All these elements collectively control how runoff is generated and drained the outlet. Besides, channel morphology and the type of drainage in an area is also influence the shape and volume of the hydrograph. Channel characteristics include the cross-sectional shape of the stream, channel roughness, storage capacity of the river channel, all of which affect the moment and attenuation of flow. Soil type as well as the distribution of soil has also great impact on the characteristics of the hydrograph. Infiltration characteristics depend on the soil type, geological formation, land use and land cover, and the presence of lakes, swamps, wetlands and other natural storage areas within the basin. So, these factors regulate how much rainfall infiltrates in the ground and how much contributes to the surface flow. The another is climatic factor. These are mainly related to storm properties including rainfall intensity, duration, magnitude and direction of storm movement across the catchment. Human factors mainly include the impact of land use, land cover changes and impact of urbanization along the drainage. Shape of the basin. The shape of the drainage basin significantly affects the time taken by rainwater from distant part of the catchment to reach the outlet, thereby influencing the time to peak of the hydrograph. When a basin is wide near the outlet, runoff from the different area reaches the outlet almost simultaneously, resulting in an early and a sharp peak. In contrast, a basin that is narrow towards the outlet tends to delay runoff, producing a later peak. Basins with low compactness or circularity often show quicker peak flows, while irregular basin shape may lead to multiple peaks due to varying travel time from different sub-areas of the catchment. Thus, basin shape governs the concentration time of runoff and directly controls peak timing. Now, size of the basin. The areal extent of a basin strongly affects runoff behavior. In small catchments, surface runoff dominates over channel flow, making land use and rainfall intensity critical in determining peak discharge. However, in large catchments, channel flow becomes more significant than overland flow. Large basins are more also produce hydrograph with a longer time base due to delayed runoff concentration. Slope: the slope of the main stream and the basin surface controls the velocity of flow. Steeper slope allows water to move faster, leading to rapid drainage of storage water. As a result, steep slopes produce a sharp recession limb due to quick depletion of storage. The overall time base of the hydrograph becomes shorter. In smaller basins, steep slopes also contribute to higher peaks discharge, since overland flow plays a more dominant role than channel flow. Drainage density, defined as the total length of the channel per unit basin area, greatly influence hydrograph shape. Basin with high drainage density drains water rapidly, resulting in higher peaks and shorter time to peak. Basin with low drainage density experience slow runoff movement, leading to lower peak and delayed peak occurrence. High drainage density promotes channel flow dominance, while low drainage density allows other hydrological processes to slow runoff concentration. Land use and land cover. Vegetation and forest cover increases soil infiltration capacity and temporary storage, which importantly delays overland flow. This delay reduces peak discharge and flattens the hydrograph. Basin with less vegetation cover under otherwise similar conditions tend to produce higher flood peaks. Among all influencing factors, land use is the most practical long-term method for controlling flood peaks throughout watershed management. Now, urbanization. Urban development increases the portion of impervious surfaces such as buildings, roads, pavements and parking areas. These surfaces restrict infiltration and reduces surface retention. As a consequence, surface runoff increases and drainage system becomes more efficient and faster. Peak discharge becomes higher and occurs earlier. Artificial drainage networks replace slower natural flow path, eliminating gradual interflow processes. Compared to pre-urban conditions, post-urban hydrographs are sharper, quicker and more intense. Storm characteristics. Storm-related climatic factors such as rainfall intensity, duration and direction of storm movement have a direct impact on the flood hydrograph. Higher rainfall intensity resulting in greater runoff volume and higher peak discharge. Rainfall duration influences the rising limb and peak of the hydrograph. Storm moving from upstream to downstream causes rapid flow concentration at the outlet, producing higher peaks. In contrast, storms moving in opposite direction generate low peaks and longer hydrograph durations. This effect is more pronounced in long and narrow catchments, which are highly sensitive to storm movement direction. Now, what are the applications of hydrograph and what are their significances? Hydrograph plays a crucial role in analysis of river discharge and water level variation over time. One of their primary uses is identifying the peak discharge and the time at which it occurs. This information is particularly important for the safe design of hydraulic structure such as bridge, culverts, spillways constructed across a river channel. Accurate estimation of peak flow helps engineers ensure that these structures can safely carry flood water without failure. Hydrographs are also widely used in the development of flood frequency curves, also known as recurrence interval curves. These curves allow engineers and planners to estimate the likelihood of flood of different magnitude occur over specific time period. Such analyses are essential for design of flood control measure, including levees, embankments, detention basins and flood walls, which are intended to reduce flood risk to human settlements and critical infrastructure. Beyond structural designs, hydrographs provide valuable insight into the overall functioning of a watershed. By examining the rising and falling limb of a hydrograph, hydrologists can assess how quickly rainfall is converted into runoff and how efficiently water is drained from the basin. This understanding supports better watershed management, groundwater recharge planning and sustainable use of water resource. A key concern in hydrology is determining not only how much water flows through a catchment, but also how rapidly it travels. So, hydrographs help address both aspects by representing variation in discharge over time. When combined with channel characteristics and topographic data, hydrograph analysis can be used to estimate flow velocity and delineate potential flood inundation zone, which is vital for disaster preparedness and land use planning. Hydrological models further enhance the usefulness of hydrographs. These models use mathematical relationships and historical data to simulate and predict hydrograph responses under different conditions. They enable hydrologists to forecast further stream flow pattern and assess the impact of factors such as climate change, deforestation and urbanization on runoff behavior and flood risk. So, this is all about today's lecture. Hope you have enjoyed it well. Thank you for watching.